And our goal is to predict that if we have electron in free space, it experiences wavy nature of its motion. The distribution originally localized will expand. And we are practicing third way to predict future by merging together eigenstates for the free space, which are plane waves, eigenenergies, which are just momentum square over 2m, where momentum can be Planck constants times this k, which is inverse wavelengths, just k index to count plane waves, multiplied by the expansion coefficient, which depends on original initial distribution, right? And the homework was to find this distribution, and then we plug it in and integrate. So I will pave main steps when needed, even simplify it and slow down, but the whole derivation with all technical details, you can find it after the end of the lecture, and I will quickly review it on Wednesday. If you do all details today, we will not fit into time. The way how to construct, how to get the answer of expanding wave packet like distribution of the wave function, is just to take Gaussian integral. And I have suspicion that you all know how to take it, and you can do it. But just in case, if anyone is not 100% sure, I will review this mathematical tool for maybe like 10 minutes or 15, and then go over sequence of substitutions, how to complete our thing and get wave function in as function of position and time found. And then I would jump immediately to the equation which shows that the width increases. More or less okay? On Wednesday, we also should sign up for next presentations. Right now, the time is not allowing us. So here is this homework. And for the first part, one just practices convolution of the function with trigonometric functions. And by definition, one needs to integrate from minus to plus infinity, but it looks a little bit discomfortable since they are repeating in the range from 0 to period. One needs to integrate only there. And one can see that in the range where the step function is equals 0, we can skip, we can stop integrating. Where it is 1, we perform integration. So basically, we integrate trigonometric function from 0 to half of the period. And then if we do have cosine, it will perform 1/4 of the period, it will be positive. Another quarter of the period, it will be negative. And it will, integral will come to 0. So any integrations of the cosine with this number bigger than 0 will give 0. So if you scroll back, all terms in front of cosine should be 0. And you still have something to compute if you didn't submit homework yet. If you look for 0 term, it will be just mean value, right? How to shift the whole function. And intuitively, as we discussed right now, we see that the anti-symmetric functions, so symmetric cosines will have 0, and sines will be half of sines will be 0, and half unknown. And those who didn't submit and plan to do it by Wednesday, just find what is the number here in this hint. So the last one means to expand Gaussian function in series of the plane waves. And the main idea of here is that one can look what is the more senior power. Who is more senior, square or just x square, right? So, and there are manipulations of changing the variable so that everything can be converted into the most senior power, right? And by these manipulations, one can convert this integral into just e to the power minus y squared, where the price for making these manipulations will be in some factors. And the this integral is like square root of pi, which I am going to spend time showing, but you do not need to listen to me. If you open Google or table of integrals, most of these things will be there. I'm just doing a little exercise in case we are staying on the inhabited island and we do not have computers, but we still need to find the propagation of electron in free space, which is not very realistic quest. Okay. So before I go to technical details, let me announce what will be the last slide. And to arrive in order to arrive to the slide, I will still need to skip some technical details, but our discussion today will be sufficient to come to it. So the result of all our exercises will prove that the shape of the wave function squared of the probability distribution will still be Gaussian, will still have this bell shape. And bless you. But the width of this Gaussian shape is controlled by the denominator in this power, like x squared divided by this denominator. And you will find that this denominator will expand. It will be initial value plus something. So I'm not vigorous enough without coffee, but I'll try to concentrate and communicate my idea. So I'm going to say something that could be more important than math that will relate to this course. And maybe if you try to listen and then take notes in your own words, it will be beneficial for all of us and for the bigger portion of the course. So when we will solve all equations, we will have the bell shape where e to the power minus x squared divided by width, and this width will be expanding. So it will be width of the probability distribution, or by colloquial language, wave packet, width of the wave packet in position space, in space of position Cartesian coordinates. Make sense? Now, if we look back on our expansion coefficients, we notice that there in the space of expansion coefficients, it's also bell shaped. And we know by our thinking or by definition that the width of the bell shape is what staying in the denominator of this power, right? And here we will take the width will be 4 divided by sigma naught, right? Or this sigma naught, our parameter of initial width in Cartesian space, will come in the inverted form. Make sense? You see it, or you need me to comment more? Yes? No? Okay, then I'll scroll back. Better we feel comfortable here. So, is this one okay? So this letter sigma is how broad the distribution is. Bigger sigma, fatter function. Smaller sigma, skinnier function. And if it is at the initial time, we can put subscript naught, 0. Now, if we perform the homework, we will get the answer that c sub k is e to the power minus k squared sigma naught in the denominator. Okay. Now, we tweak our mind that if we see Bell function, we can identify exponential, we can identify square of the independent variable, and then anything under the sign of denominator will correspond to width in the appropriate space. So now we are in the space of variable k, and here the denominator, you can think about it as minus k squared divided by 4 divided by sigma naught. So width in this k space will be 4 divided by sigma naught. Make sense? Okay. Oh, I already wrote it here years ago. Now, the important thing that may have philosophical connections for the future. And I do not see any logical way to explain, just as an experiment. Let's multiply width of the wave packet in the Cartesian space, in the X space, and width of the wave packet in this strange momentum space, in space of this. So we will multiply it sigma naught times 4 divided by sigma naught, right? So we'll get a constant at time 0. But if we find that at least in Cartesian space, the width is increasing, then the product of the width of these two widths will be growing. And this I will return back to it, but let me introduce it right away. So width, product of this width will be increasing. And it is a fundamental property that will be correct for many other examples, not only for free electron in space. So which language one is using to talk about it? So the width, if we are talking about like grades in freshman courses, how do you call this width of distribution? Standard deviation, and any other a little less scientific, like what does it mean, standard deviation?
Like how much the data deviates from the...
Okay, so how much the data deviates from central value? If the deviation is small, it means your results of your multiple experiments are certain. If it is broad, it means results of experiments are uncertain. So it would be not wrong to call the standard deviation uncertainty, right? Now, if we go forward and speak about uncertainty to find position of electron in position space, and then uncertainty to find electron in momentum space. And then we multiply it. So it will be combined uncertainty to find electron simultaneously in position and momentum, right? So this combined uncertainty to find simultaneously position and momentum of electron will be always growing. So since t squared is positive function, even if you design time machine, it will never get smaller than predefined constant. So no matter what we do, uncertainty of simultaneous measurement of position and momentum is not possible. It will always grow. Now, please try to make your notes maybe just in one sentence as you can, and then let's try to read. I believe it will be much more important than this boring mathematical exercises. Look over the folder.
Sure.
Okay. Yeah, keep going. Keep going. Now look over the shoulder. Look over the shoulder. Is it okay for you to look? Okay. Okay, so let's try and listen to each other, because I'm not very skilled in giving exact formulations, and I believe that your attempts to verbalize the statement will be much better and clearer.
I didn't.
Just try your best.
Okay, I basically wrote down the first sentence: width of the distribution is referred to as uncertainty. The larger the value of the standard deviation, the more uncertain. Then I wrote down the equation and just described what each variable is.
Okay, yeah, thank you, Nate. Well, would you try either to read or verbalize as you understand this?
So the Gaussian distribution, the deviation from the center is known as the uncertainty, and which is like future position of electron. So it's uncertain to know the position of, I don't know.
Yeah, everything correct. And there is a second part. So it's uncertain to know the position, and it's uncertain to know the momentum. And you cannot do it simultaneously. Yeah.
So I wrote down basically just sigma naught gives the uncertainty, and the product of uncertainty in the spaces of position and momentum will always be greater than or equal to a given constant, and the larger values are more uncertain, whereas the smaller ones are more certain.
Yep. Listen, Sibyl,
It's okay. So basically, I said that basically the width behaves like an uncertainty indicator. So basically, by multiplying the uncertainty to find an electron in a position in space and the uncertainty to find in momentum will give us an increasing uncertainty that will always keep on growing no matter of anything, I guess.
Okay. Yeah. Thank you. Right. Your interview.
I said uncertainty is always increasing and increases with time and can never be less than the constant, which determines the uncertainty of the position and momentum. And uncertainty can be visualized like standard deviation.
Okay. Yeah. Thank you. So those are great statements. Probably I like them better than what I was trying to tell. Are there any from Ellison and Josh? Would you like to speak? It's not mandatory, but if you like to speak, it's your chance.
Nope, I agree with what everyone else said.
Okay, thank you. Josh, do you have your version? Version 1, version 2, version 3? No version. That's fine. Okay, I am going to return to sharing screen, and I think there is something in chat. I agree with okay, yeah, thank you, Josh. Whew. So the fun part is over. Unfortunately, now we'll go to boring math. But we will return to this idea again and again in different verbalization and different ways, different implementations. So here is the stuff that we are trying to do, right? That you did a quiz, right? And here is how we are going to proceed it. We can set up a dictionary and bring this into the form of, again, exponential with several powers, and you will look onto the most senior. And in order to come to this shape, we can identify A capital as everything in front of the k squared, which will be this part, h bar over 2 masses times time, and minus sigma naught over 4. So this is A capital, and you already see it does carry the dependence on time. Right? Now for the B, it will be the coefficient in front of linear term. It will be quite simple, minus ix. And C will be, multiplier will be square root of sigma naught pi, which comes from the solution of the homework. Why I'm going to show these details? It brings us to analysis that you already verbalized, and taking the integral either forward transform or backwards transform, it's same type of integral. If you follow these steps, you do homework easily in a couple of lines. So sigma naught is width. We already agreed. Now, if you deny to find the answer in Google or in a table of integrals, which I doubt, but if I deny to look into Google, how can I take this integral of e to the minus variable squared? What's the integral of Gaussian function? Does anyone memorize from heart?
Isn't it like square root of pi?
Yes. Do you know how to prove it?
I was no.
Okay, I'm going to show it if you care. If you don't, you just relax. So and it's quite a simple thing. but it's impressive. The proof may appeal to you even if you hate math, because it goes very non-linear logic, even from the first line. So suppose we need to find integral minus x squared dx. No one forbids us to rewrite it as second integral, where it will be minus y squared dy. And no one forbids us to, just as a little exercise, to find I1 times I2, right? So these two integrals should give the same result, right? And if you find integral I1 times I2 and take square root, it will be whatever we need. Okay, now let's look on it from geometrical aspect. This I squared will be e to the minus x squared plus y squared, which is a radius, right? And why we all are doing it? Because one cannot change variable of integration, because like here is x squared, here is x. If it will be like e minus x squared times x dx, one could submerge x squared under differential sign and do it immediately. But here is uncomfortable for front attack. But if you look, let's look on the geometrical argument. So it's e to the power minus radius squared times dx dy. So what is dx dy? It's product of two infinitesimal increments. So if dx is length, then dx dy is area, right? So our I squared is integral e to the minus r squared times element of area, right? Now, what is the area of a circle? Yeah, correct. What is the change of the area of circle if we expand the radius? So, and I skip this coefficients. Suppose it's just r squared. So derivative of you can keep pi r squared over dr. So from second power, it will come to the linear, right? Yeah, it's better to be rigorous. So if we take this derivative and then multiply left and right side on dr, we will see connections between derivatives of area and radius, right? And we can return, we can replace the increment of area to the increment of radius times increment of angle. So if it is the full circle, then it will be 2 pi, right? If you have just a fraction, it will be d phi, increment of angle. And then it's increment of area in polar coordinates. So radius times dr times d phi. You want to believe me, you do not want to believe me, you have doubts if it is a good way to go. Okay, so everything is made for the purpose of unavailability to make a frontal integration. So when one makes a bypass, that does work. And through geometrical arguments, through performing integral on a plane instead of linear, one can get the answer and be happy. Okay. So our I squared will be integral over phi, integral over radius, e to the minus radius squared r dr d phi. Integral over d phi will be 2 pi right away when can get it. Right? One can separately treat integral over d phi, and then we do have e to the power minus r squared r dr. This is much more comfortable. You can, we always remember that integral of r dr will be r squared, and one can do this, how do you call this procedure? You just change variables, right? If you do dr squared, we come back to this thing, and we can use r squared as our new integration variable. So we will rename r squared as u, and 2 in the denominator is a price for converting from r dr to dr squared. And now we will call this little blue circles as u. And then we will have this cancellation of the 2 from change of variables and 2 from 2 pi, we will get pi times integral from 0 to infinity u e to the power minus u du. Make sense? Or you need more comments? Okay. And then integral of this e to the power minus u in the limits from integral of exponential is exponential, right? And we need to export in the limits from 0 to infinity. At the infinity, e to the power minus infinity will be 0, e to the power 0 will be 1, and 1 and minus 1 cancels. So integral itself will be 1, and we have a prefactor of pi. So the result is pi. But this was our I squared, geometrical integration of Mexican sombrero hat in two-dimensional. But now we need to take square root to get our one-dimensional integral, which will be just square root of pi. Make sense? Square root of pi. So now we have 2 ingredients for our physical chemistry reaction. One ingredient is integral of bell shape, which will be square root of pi, and another that in fact we need to take this e to the minus polynomial, right? So we could take this integral if we change variables in the following shape: e to the pi minus y squared dy, new variable. So we need to identify such variable, new variable, that we can put here as square and here as linear. So we need to do some trick in variable substitution. So here is another. It's very non-straight logic. If I wouldn't know the steps, I'm not sure I would do it, or I would do it quickly. But in our middle and high school algebra, you all did practice this square of sum, right? Now let's identify similarities between polynomial in the power and this equation. So we have squared, we have linear term. Here we have squared, we have linear term in variable a, and then one more. So if we could convert back from polynomial to square, then this everything inside these brackets could be our new variable. But it is missing. We cannot do it literally, right? But here is logic. No one forbids us to add and subtract the same number or the same function. So what if we add and subtract such thing so that this polynomial will be possible to bring into this square of sum? So this leading term can be thought of as square root of a squared times k squared, right? So that will square root of a times k squared. Square root of a k squared. And in our linear term, we want to identify the same variable, which we'll call lowercase a k square root of a. But in order to bring it just to the factor b, we divide it by square root of a, and we also multiply divide by 2 to match literally equation of summation of square of sum. So in this representation, we will have little a squared plus minus 2ab. What are we missing? We are missing little b squared, right? So we just add. So our little b is this big b divided by 2 square root of a. So we add this little b squared and then we subtract this little b squared, right? So I'm free to do this exercise. I'm not breaking mathematical equality between things. And now we can look on the first 3 terms, a squared minus 2ab plus b squared. They will be condensed into square of sum. And this thing does not depend on k, on the integration along which we integration variable. So for the purpose of integration, this term is just a constant. So we can rewrite it in the front of the whole integral. So it's kind of our penalty function to make this transformation. And then under integral, we have e to the power a squared minus b, this. And at the front, we will put just a constant. For our final result, this constant will be most important because uppercase a contains time and the answer will be there. But to be mathematically rigorous, we need to perform this identification of the full squared. And then we will bring it to integral of Gaussian, which will give us just square root of pi. We already know the answer and we just need to do it in the organized way. But this price for the trick will contain the answer. And the rest will be just carefully bringing everything to square root of pi. So it looks this way: full squared and additional term. Yeah, it's square of summation. We can identify that each of them have minus, and then here will be plus. Okay. So this term will go up front. Everything under integral will make transformation to new variables, e to the minus y squared. And by transformation of, and then it will give us the square root of pi. And the free term original multiplier and another thing from transformation of variables here will be our answer. If you are meticulous and rigorous, you will be unhappy and unsatisfied for missing details. But based on time, we better rush to just looking on this answer and analysis, and missing details will be provided at the beginning of Wednesday meeting. So top line is the answer, and now we need to roll it back into readable form that can be interpreted scientifically. So we apply this dictionary where little a, little b, capital A, capital B, and C. So one plugs in all things, and most important thing will be, so b squared contains capital A, lowercase b contains capital B, and capital B contains this time evolution. So if we carefully substitute all these things, which I promised to do on Wednesday morning, the wave function will include exponential, where the nominator of the power will have x squared, and the denominator will have this original width plus I some factors times time. So if you look on the wave function, it will be something not quite comfortable. It will be imaginary unit in the denominator of Gaussian function. But if you take absolute value square, if you take psi star and psi, if you multiply them, then the imaginary unit will multiply I times minus I. And instead of fringes due to imaginary unit, it will be just homogeneous growth in the next power in t squared. So actual, good, 1 minute for actual lecture. So the answer of the probability distribution will look this way, and we should look on the denominator. Here is initial width, here is combination of the constants, Planck constant, the mass, and here is time squared. So we extract thing from this denominator and start analyzing it. So width is increasing over time. It's increasing quadratically. Wave packet becomes fatter and fatter with time. If you multiply it with widths of the in the position space, we get an idea that it will never be smaller than some predefined value, which means one cannot simultaneously measure position and momentum. Meeting is done. Everyone is welcome to disconnect and depart. I'll stay here to answer any questions. Yeah, we are in time.